Hello, and welcome to another wonderful lesson with Mr. Wheezy. Today we're going to be getting into Chapter 3. Chapter 3 is going to be all about what can we do with derivatives. Starting with Extrema and interval. But before we do that, here we have the kickoff. So the kickoff, you're pretty much going to do the derivative of the equation. Remember, since we are doing this with terms of t, anything with a y will get a dy dt. Everything with an x will get a dx dt. So when you do this derivative, you'll end up with dy dt equals 2x dx dt. The 3 goes away because it would be 0. And then you're just plugging in the values and solving from there. So, big definition of extrema. Long story short, extrema are just where you have maxes and minimums. That's what extrema are. So like number 1 is saying it's going to be the minimum if all the other values are going to be less than the value you would get at this point. It's going to be a maximum if all the other values are bigger than what you would get at this point. So, that's going to be your extrema. They're called relative extrema if it's just the high or the low in that area, and then the absolute extrema if it's the high or the low for the whole graph. So like say on a parabola, you would have an absolute minimum because that's the lowest point of the whole graph. Whereas if it's doing some squiggles, each little part might be a relative maximum. However, there's another part that could be higher further on down the line. So, the extreme value theorem. If f is continuous on a closed interval AB, then f has both a minimum and a maximum on that interval. So, extreme value theorem, all it's really saying is if we have a closed interval, so there's no places where there's a jump, a skip, whatever. If we have a closed interval, somewhere is going to be a max, the high value, and somewhere there's going to be a min, a low value. Maybe it's in the middle, maybe it's one of the endpoints, but somewhere there'll be a max and somewhere there will be a min. So as far as relative extrema go, it's just going to be on a smaller interval where there's going to be a max or a min, and we're going to get into it here in a little bit. So find the value of the derivative at each of the relative extrema. So first thing you're going to do when you do these, and we're going to get into a little checklist here momentarily. But just know for right now, we're just going to kind of go through the steps of it, and then we'll get really full on into it here. So first thing we're going to do is you need to find the derivative. So here we have stuff on top and we have stuff on the bottom. And so we're going to end up doing the quotient rule. So quotient rule is derivative of the top, which would go to your x squared would be 2x times the 9, so this is really 18x. The minus 3 would go to 0. So it should be that times x to the third. Then we minus the top, so 9 times x squared minus 3 times the derivative of the bottom, which would go to 3x squared all over the bottom squared. So if we simplify this first part will be easy. We just times the 18x in there. So we'd have an 18x to the fourth. Minus here, we would distribute actually both ways. So 9 times x squared times a 3x squared. Well, 9 and 3 would be 27. X squared and x squared would be x to the fourth. 9 times 3 would be a negative 27. Negative 27 times 3 would be 81. So minus, which actually is a plus with the minus up front, 81x squared. Bottom then, well, x to the third squared would be x to the sixth. So we can simplify this out to 81 x squared minus 9x squared, fourth, sorry, over x to the 6th. And then we can get rid of some more. There's 2 we could cancel out here. Just go to squared. So this end up 81 minus 9x squared over x to the 4th is where this goes. So, with that being said, now from here then we would go ahead and start finding values of those extrema. So on this one here, 3, 2 is actually one of the extremas. We'll get into how we get that here momentarily, but for right now, let's just look at this being an extrema. So if we put x into here, 81 minus 9 times 3 squared over 3 to the 4th. Well, 3 squared would be 9, and 9 times 9 is 81. So 81 minus 81 would be 0 on top, so it really doesn't matter what the bottom is. If the top is 0 on a fraction, the whole thing will then be 0. So what that's saying is f prime of 3 is going to equal 0. So that's where one of these extrema are going to occur, is when the derivative equals 0. The other side of this, absolute value of x. So if you think about absolute value of x, the graph of it looks like this. So if you think about it, the limit here won't exist at 0, because this is sloping down, this one's sloping, or this one's sloping down, this one's sloping up. They're not, your one side limits aren't going to be the same in this case. So therefore, x equals 0 is going to be a relative minimum also. So here where x is not differentiable is going to be another spot where these extrema are going to occur. So where the derivative equals 0 and where it's not able to find the derivative, those are going to be spots that we're going to look for these extrema. And those spots that we look are called critical numbers. So let f be defined at c, f prime of c equals 0, or if f is not differentiable at c, then c is a critical number of f. So anywhere where the derivative equals 0, anywhere where we can't find the derivative of, that's where we're going to get these critical numbers. Theorem 3.2, relative extrema occur only at critical numbers. So that's telling you straight up there that these relative extrema will only happen with these critical numbers. So we're going to find these critical numbers, test them, and then we'll find, okay, which one is our extrema then. So here are the guidelines for finding extrema on a closed circuit. So first thing is you're going to find those critical numbers. Then we're going to evaluate each critical number into our function and every endpoint of that closed interval. Whichever one is the lowest is the minimum, and whichever one is the biggest then is the maximum. It's really going to be that simple. So, start by finding the derivative. So derivative here, x to the 4th, we bring the 4 down. 4 times 3 would make this 12x to the 3rd minus, bringing the 3 down, another 12, x squared. Is going to be f prime of x. So next we need to find all values in which the derivative there will equal 0. To do that, take your deal here, your derivative, and set it equal to 0. So we have 12x squared we could pull out front. That would leave us with x minus 1 inside equal to 0. So 12x squared equals 0 and x minus 1 equals 0. So if we solve, x would equal 0 and x would equal 1. So these are going to be our critical numbers. There's really no place where we couldn't find the derivative. So in this case, these are going to be our only two. But we'll also check those endpoints too. So we're going to do we put that back into the original. So f of, well, our one endpoint's -1. Then we have a 0, 1, and our other endpoint would be at 2. So endpoint, critical number, critical number. So that's what we're testing here, is our endpoints, which was at -1 and 2, and then our two numbers that we got when we found where it's equal to 0 is 0 and 1. So if you put those in, now easiest way is going to be, if you have a graphing calculator, to put this in your y equals. So I'm going to clear out anything that I have here, and we're going to put this in. So 3x raised to the 4th minus 4x raised to the 3rd. So let me go file table, or second table. And I'm going to clear these out. You'll have to delete them, not clear. And so then we can put them in -1, 0, 1, 2. So have our values there that we can write down. 7, 0, -1, 16. So here's our minimum. Lowest value is -1, so that's our minimum. 16 is our highest value. So this is our max. So that's how we're going to go about finding these. This is all we're going to focus on today, is just finding where these critical numbers are going to happen. As we keep going with these lessons, we're going to get into more stuff as to, okay, well, what else can we do with it? How does this all build into something? So find the extrema of 2x minus 3x 2/3 on the interval from -1 to 3. So first step, f prime of x. 2x would just go to 2. 3x to the 2/3, you'd bring 2/3 down. The 3's would cancel. So you have 2x to the -1/3. So from there, we would then go through and, well, could we solve? Well, yeah. What will make this be 0? Well, so number one, this is to the -1/3. So keep in mind, this is really 2 over the cubic root of x. So right now, to make this be 0, if we put a 1 in here, cubic root of 1 would be 1, 2 over 1 is 2, 2 minus 2 gives us our 0. So x would be 1, The other side of this is if we put a 0 in here, that would cause that to be problems. So that's where the other number that we're going to use for a critical number to be 0. So numbers that we couldn't find the derivative of is if we put 0 in here, that would be bad. Plus, if we put 1 in, we're going to end that top to be 0. So those are our critical numbers. We're also going to check endpoints. So we're going to put these in. Same sort of a deal. Put them into your y equals. If you do that, you're going to get -5 here, 0, -1, and -0.24. So -5 is your min, and 0 then ends up being your max. It's going to be the high point of it. There's your extrema. On to the fun one. But hey, then we're done. This is the last one. So, first step, find the derivative. So, f prime of x. Derivative of sine goes to cosine, so this would be 2 cosine x. Cosine goes to sine, but it switches the sign to be a plus sine 2x. Because this is a 2x and not just an x, we have to do chain rule with it. Derivative of 2x would go to 2, so I can have that in front. And that would be our derivative here. So, where would this equal 0? So if I remember right, I did not assign you one of these just because these get a little more complicated like this. This is something that really would be good if we were in class to be able to work through these. So I'm going to do some magic here instead of explaining and really confusing you guys. Because to really define what this is, we want to use one of our trig functions, trig identities that we did in advanced math. And again, with not being here, it's just going to be more confusing. So long story short is you would go through and your x's that you would get would be pi over 2, 7 pi over 6, 3 pi over 2, and 11 pi over 6. So you go through and you check those. We'd have our endpoints here. We're really restricted from this. So you do f of 0, f of pi over 2, f of 7 pi over 6, f of 3 pi over 2, f of 11 pi over 6, and f of 2 pi. So when you do that, you get -1, you get 3, this would be -3 halves, -1, -3 halves, and -0.24. So we have 3 here, which is well above everything else. So this is our max. -3 halves is our lowest. There's 2 of them, so there's actually going to be 2 mins in this case. The reason I want to show you this one is if you do get multiple mins, that's okay, or multiple maxes. If they're a couple, if there's more than one, let's go that way. If there's more than one that is the same value, that's either your max or your min, you can have multiple. It's okay. So that's really what I wanted to show you with this. Again, I don't believe I assigned you one with trig functions. If I did, you can skip it. I will give you permission right now. Just because that's going to be one. It's really would be much better where we're in class where we could really sit down and work through it. And it's going to be harder to do that over the internet. So that's what we're going to do there. Questions, comments, concerns, please let me know. Shoot me a message on Google Classroom, email, or Pan, although Pan's going to be one that I don't check as often as the other ones. So definitely shoot me a message. A lot of you have been doing that already. Keep that up. That's what we need to do to get through this. But until next time, we'll talk to you later.